So in this video, we're going to cover wrapper-based approaches and embedded approaches in the realm of supervised techniques for feature selection. If you're interested in filtered-based approaches, I have a link in the video in the description below. So first, let's talk about wrapper-based approaches. So wrapper-based approaches is essentially like using a special helper to pick the best things. It's like having a friend who tries different toys and tells you which ones are the most fun to play with.
Will it blend?
The helper will test the different toys and tell you which ones you should play with because they're the most exciting and the most enjoyable. The helper in this case is a specific machine learning model that you're going to use to determine the most important toys or features in the dataset. So now we're going to cover 4 wrapper-based approaches. So we're going to stick with this toy analogy and explain the first one, forward selection. So first we start with one toy and we see how much fun it is. Then we add another toy and see if it makes things even more fun. And then we just keep adding toys until we have the most fun collection to play with. So here's some code that kind of illustrates what I'm talking about. We're trying to find the best features using logistic regression. And when we graph the number of features needed to get a specific accuracy for our model, we get something that looks like this. So we can basically say that, if you have 4 features, you have an accuracy of 95%. So the reverse of that is backward selection, and that's our second technique. It's the opposite of forward selection. It basically begins with the full set of features, and then it starts removing features one by one and basically just removes the one that doesn't really contribute to the model's accuracy until it gets to an optimal subset of features that are left. So you can see a visualization that kind of looks like this. Exhaustive feature selection. This is a method that evaluates all possible feature combinations to identify the subset that gives us the best performance for a specific machine learning model. So here's some code that illustrates this implementation. It uses a function called exhaustive feature selector using a random forest model to do its work. So what you can see in the output is essentially the model's accuracy when you have certain combinations of features found in the dataset. The fourth technique is called recursive feature elimination. It's an approach that starts with a subset of features and then adds or removes features based off of their importance. Okay, so now let's talk about embedded approaches. This is kind of like having a smart robot that can learn and choose the best features for a task all by itself. The robot builds a model as it learns, it figures out which features are the most important, and only keeps those. So there are 2 techniques in the embedded approach. The first one is called regularization. It's like wearing a seatbelt while riding a bicycle. It helps you stay safe by preventing you from going too fast and losing control. This technique is used to prevent models from becoming too complex and overfitting the data. The second technique is called random forest importance. It's sort of like asking a group of friends for advice. Each friend has their own opinion, and some may be more knowledgeable than others. Random forest importance looks at all the opinions from all your different friends, aka decision trees, and combines them to figure out which factors are the most important in making a decision. It helps us understand which factors have the biggest impact on the outcome, just like when we ask our friends for advice and consider the opinions of those who know more about the topic. So that's it for now. We've covered 3 main supervised categories, and within those 3 categories, we explained a few techniques you can use to select your features for your model. If you want to know more about each technique, follow the link in the description.